Hi everyone, Justin here. This is part 3 of my screencast series about how I practice test-driven development, as I call it, discovery testing, where we start from the outside in. We try to use TDD as a means to help break big problems down into small ones. The theme of today is we're going to tackle the next piece of the puzzle, but I'm going to intentionally work in a slightly too large of a step and not necessarily bake in the same amount of thought into how to break up the behavior and show how that can lead to some pain as we try to undergo this. We're going to actually muscle through that pain today so we can see how we would work through it. But the actual way that we respond to pain whenever anything's hard to test or we start to find that these objects that are collaborator objects start to end up with too much logic, the feedback should be, hey, maybe this is doing too much. Can I imagine a new dependency? But in order to really appreciate that, I think it's necessary to kind of muddle through and push through a little bit. And I think this next one's a good example because it's exactly what I did, even though I have a lot of experience with this, and I found myself banging my head against a wall with how much complexity I was adding to this one little object. So this is where we were yesterday. Simulates Conway is the object that we tested in the first round, and all these four other things, the world and the three things below it, are objects that got shaken out through the processes of what I call just fake it till you make it. Let's just imagine new things that do this work for us, and our job is simply to specify the inputs and outputs of those things, as well as the values that float between them, instead of thinking about what the actual behavior needs to be inside of each of those things. Well, that layer is done, the top layer is done, and now we have to pick which of these three things to work on underneath it. Because it's the riskiest and it's the most complicated, we're going to look at the replaces world one, which is right under the second. This is the job of this piece, I suppose, is going to be takes a world as input, needs to be able to return the next generation of that world with all those cells and their alive and dead states for them and all their neighbors. And what makes this really tricky is that we've decided to go with an expansive approach where, in order to respect the requirement that this is a limitless, infinite grid, we're going to impose a time limit on ourselves. So we're going to just be kind of discovering as much of the grid as we can in one time limit and then quit. Okay. So if we just focus in on replaces world, because I was stressing about how to implement the time limit in a way that's not going to muddy up all my logic, I kind of overemphasized while I was planning the first time around. I'm going to walk through my thought process. So here, because I'm really worried about how am I going to do that time limit thing well and model it in a way that makes it easy to test, as well as just sensible to model in ways that necessarily decouple us from time itself, so it's easier for us to exercise the code and see what it's doing. So I was thinking about that a lot. So then obviously the first unit that I think of is I need something that keeps time for me, can answer me the question, is my time up or not, without me doing a bunch of silly math subtracting milliseconds from each other. So that means that I'd want some kind of value object off to the side called maybe a time limit. And then when I got to thinking other responsibilities this has, I just really thought, well, I need something obviously that replaces each individual cell. What I should have done probably at this step is think, replacing a cell is kind of like the rest of the application. That's pretty loaded. Is there anything else here? Is there anything iterative? For example, how do I find the neighbors on those cells? How do I iterate over those neighbors? How do I tell the contents in those cells? And I wasn't thinking about those things because I was so focused on the time question, and I should have responded to the pain that I ran into when I was trying to test this earlier by backing up, but instead like I mentioned earlier, just muscled through. So here's a good smell of that as we talk about how these things interact with each other. First off, we have this thing called replaces world. That means we need some kind of mutable world. We receive a world as input. We're going to make a new world, but we need to be able to iteratively, since we're under this time limit, keep on plopping in new cell values at various coordinates throughout the world, which means we need a concept of coordinates, and that means that now this replaces world thing has an additional behavior, which is needs to figure out where to start when it's replacing a new world. We'll start at the origin probably, but that's just another little bit of complexity that we need to worry about, which is worrisome as this gets more loaded. So it starts off, we're going to keep a time limit. This keeps time thing should return to us a time limit that we can interrogate frequently. We'll ask it right off the bat, hey, do I have any time left? And if I do, then I'm going to go through this replace cell. And like I said, I'll probably pass in coordinates to that initially, and the world object, so that it can go and find the neighbors of that particular cell. Coordinates we'll start with are the origin. And then replaces cell should probably just continue to be called over and over again as long as there's time left. That means that when a cell gets replaced, we need to return not just the outcome, the new contents that go inside those new coordinates at that world, but the return object, the result object of replaces cell, needs to also contain the neighbors. That way we can continue to fuel ourselves with new work. That means that every time we do a cell, we need to go take all those neighbors and, I don't know, shove them onto a queue or something to be iteratively processed as long as time allows. And then as soon as time's up, we'll just return that mutable world as it is back to the top of the app. So we have this concept of contents. You could call it an alive cell or a dead cell or a point or what have you. But because I'm imagining this like a petri dish and a grid, whatever is in one particular cell's coordinates, I'm just considering the contents. So that's some kind of super type, and you might see nothing inside of it, or you might see a cell. So this concept of an outcome might combine the sense of here are the next contents for this particular location, as well as here are the neighbors. And those neighbors might reuse those types. They'll have to carry with them coordinates as well as their current contents. So all that to say, this is a lot of value objects shaking out and not a lot of behavioral objects, which is somewhat worrisome. It should have been more worrisome to me if I'd been at a whiteboard instead of an airport lounge just hacking at this a little bit too late in the evening. So we're going to take a stab at this. If you look over in the left, we have now a whole bunch of high-level stuff, and it's not really clear how it interacts. One thing I like to do, just like in those trees, I like to stick my values off into their own directory so it's clear that's what those are. I'm going to drag the world up here into a new package called values and trust that Eclipse is going to make sure nothing gets broken. Also going to update package presentation to hierarchical so I don't have to read the same redundant word over and over. Alright, so generates seed world thing, outputs world. We'll punt on those for now. Simulates Conway being at the top level, makes it obvious what it is. This replaces world. We already can predict a lot of stuff's going to shake out of it, so I'm just going to put this all in a package called replace. The package itself is not significant to me. What matters is that whatever tree-like structure of objects that I have, that the code is organized in a way that it respects that tree. Having a beautiful whiteboard of this great object descendancy is really useful, but then if all that's left behind is this code that's just in one big flat folder called models, you're going to be pretty much out of luck to try to piece this all together, except for at runtime. Alright, so I've got this replaces world thing. This already existed. I'm going to hit Control-J to generate a test for it. Replaces world test. Notice we're on the same symmetrical package. I'm going to use my Makito helper here. Alright, because I know this is definitely a collaborator object, so it's going to use test doubles of its dependencies. Alright, so this is a replaces world. First, and again, overemphasizing my fear about the time limit thing, I want an object called keeps time. Throw this in the main packet, main source folder in that replace package. And something else called replaces cell. Oh my goodness, replaces cell. I have to go ahead and create that as well in the main package. All right, cool. Now when we get to the actual test, the way that I'm thinking of it is, if you look back in the presentation, when I was drawing this out, there is a base case that might help us write a simple test to get some of the plumbing going, and that is when there's never any time at all. So as soon as we make the time, we're out of time. So time for 0 iterations. I guess iteration is a bad word because it sounds like generation. Time for 0 coordinates to be processed. I'm going to say cells to be replaced, so we use the same kind of language. Okay, so that means that when I call keeps time with, I guess, keep, then it should return me a time limit. Time limit, I'll set up a local here. create local. I don't want it to be a generic object. I want it to be a time limit object. Oops. And I'm creating it in my test side so I can configure it over here. Put this in the main package. And the time limit object itself is going to probably involve, like, you know, taking an actual time when you pass it in, and then returning, you know, true or whatever by doing actual math on actual milliseconds. So that value object is certainly useful, but if I use a real one, it's going to make this test more difficult. So I'm going to actually use Mockito to mock out a time limit for me. Normally I don't mock my values unless it's in cases like this, where it would be hard to test with a real instance of the value. Alright, so I got a time limit, I get call keep. Keep doesn't exist. Now I can generate keep and get the, well, one would hope, the method signature I want. Alright, so if I call that, then my action step is to say, this is already developed, right? So the API, the entry point of this class has been decided by the person who needs it. So we don't have to reinvent that here. We know it takes a world and a time limit. I can see that because the naming, calling this time limit isn't helpful, so I'll call it time limit in milliseconds. And in fact, I'm going to hop in here, and so I don't run into the same thing. Call that there as well. And here, it doesn't matter what we punch in again. So I'm going to just say that's 42. And in fact, because time's recorded in longs, I'm going to adjust this signature and see that nothing breaks. And hopefully nothing broke. Okay, so old world. So if I call that old world, and maybe I'll just call it world 1, since ultimately when we run these tests, we're going to probably do 1 and then 2 rounds as well. So if I'm calling to replace world 1, I'll need a world 1. Let's create a new world for us. I won't need to actually use replaces cell at all, because if I don't have time to replace any cells, it's not going to get invoked. So then I guess all I'd really assert, remember that this is a function that returns the most recently replaced world. I always call whatever, my return value is from my act step, I always call that result, or results, plural. So now I can use a hamcrest matcher to say assert result is world 1. There's no time to change it, so we're just going to return the world back that we already had. So that's a nice simple base case. Okay, but was null. So that gives us enough runway to start implementing old world and now I could absolutely just do this. If I was practicing Detroit School TDD, I'd probably do this, use it to triangulate and build a lot of test cases. But because I really want to, let's see, because I really want to like just specify this interaction and get a little bit of progress before things get crazy complicated, I'm going to go ahead and humor myself anyway by using the dependency. So yeah, cutesy triangulation is something I don't tend to do a whole lot when I'm in a collaborator test. All right, so keeps time keep is going to give us a time limit object. I guess keep needs to receive the time limit in milliseconds, so it can know. So that's not super helpful. So we're going to change the method. That means that, oopsie, did that split thing again. Oh no, it's not going away. All right. So that means that the test is going to be wrong. I'm going to say add argument, and I'm going to make it the same argument so the stubbing gets satisfied. 42L, just some arbitrary silly number. So if time limit, I guess we're saying is time up is how I've been saying it, but all right, we'll just call it time's up and we'll do a not. Or I'd rather phrase that affirmatively since we're about to do stuff. Time's up. Returns a Boolean, great. It returns false in fact, by default, but that false is a trick, right? Because this time limit that's going to get returned by keep here is actually a mock object. And so it's going to return whatever we stub it, regardless of what its implementation says. And then we say, well, do this later. This is going to be a later test. And we're just going to return the old world for now. So that's a start. See if we pass. Okay, test is still passing. We have a little bit more structure in place. Obviously, we need to write another test now to shake this out. So if we only have time for one, we're going to use kind of some of that starting point that we've already built up to specify what we want. So I'll have another time limit, but this case, this time limit, oh, right. So Mockito by default provides falsy values to everything. So time limit being a mock, having a Boolean method, Mockito will by default return false. So I didn't have to actually explicitly stub it, but I probably should have for the sake of clarity. Time's up. Oh, in fact, you know what? It's true, right? So I really should definitely stub this. When time's up, then return true. And the only reason that didn't blow up previously was because this was a no-op. But if I'd been throwing here or something, or put it in unfinished code, it would have blown up. So just again, that test was there mostly for the plumbing sake. Definitely doesn't provide us a whole lot of confidence that the collaborations we want are ready. All right, so next up, we're starting where we did before. So time's up. Now, if we want to do one cell, that means that we need to return false first, and then subsequent invocations should return true. This multi-vararg thing on then return is a Mockito trick that lets us do sequential stubbings. So the first time time's up gets called, it'll return false. It gets called again, it'll return true each time. Let's see. World 1 is new world, and now this stubbing will actually start to make some sense because we'll have a world 2 ultimately. And you know what? That world 2, that mutable world, is probably going to get instantiated by our subject, so we're not going to be the ones to create it. So let's think about the other stubbing we know we need. So when replaces cell gets called with replace, what gets passed into replaces cell, and what does it return? I talked earlier about how it needs to return both the contents of that cell as well as the neighbors. And I'm going to, instead you don't like multiple returns, so I need some kind of argument object or parameter object that can come back as one thing. So I'm going to call that an outcome, and it's going to contain the next contents for that cell, for that coordinate, as well as the neighbors, a set of neighbors for that coordinate, so that I can keep working. I'm going to call that an outcome. It's going to be a long test, I think. This is just going to be a marker class until we know what to do with it. Okay. Now replace needs to take some initial cell. I guess it's going to be a coordinate of a cell. Which we're going to need some kind of coordinate object that has implements equality checks based on x and y. So I'm going to call it coordinates, and it's going to take an x and a y. I could, of course, pass in primitives, but whenever I can avoid passing in primitives, I do that because these things tend to get more complicated over time. So I'm going to go create coordinates. I'm dumping these in replace right now. I probably should dump them into a replace.values, but for now I'm going to keep rolling ahead. Okay, so if I call replace at some coordinates, it also needs the world, so it's able to go and discover those neighbors. We don't know how that's going to happen yet, but that's going to be part of the job of the replaces cell. We've got enough going on here. So we're going to pass in world 1. Create this constructor, xy, integer xy, this.x = equals x, this dot y equals y. And like I mentioned, we wanted to make sure that the equality checks work, so rather than implement that on my own, which I'm not to be trusted to do, generate hash code and equals here. So, yeah, that's disgusting. So, mark that. Generated code, so people don't try to maintain that too carefully on their own, and just regenerate. Okay, now I'm ready to create this method signature, and we're going to say that this returns an outcome object. And it looks like it only got the coordinates piece. It didn't get the world piece, so we want to provide that as well. Now what? Oh, too many parentheses. Makes Jack a dull boy. Okay, cool. So there's that stubbing, and now just through the process of doing that stubbing, we've realized that this job of figuring out which cells we need to replace is probably bigger than we anticipated. This assertion is also going to be wrong. We're not asserting that a world is a world. We're going to be asserting instead stuff about that world. So the outcome is going to need to have contents. So when we look at whatever the result is, if the result is a world, we need a way to look at a particular point in a world, get its contents back, and we want those contents to be whatever the contents on outcome are. So outcome needs a sense of new contents. Create a new class called contents. Again, those contents might be a cell that's alive or a nothing, which is just an emptiness. All right, so now we need to start filling out that value. This dot contents. So Java being Java means that we have a lot of this kind of boilerplate to work on. The IDE gives us a lot of help, but part of why Java is a useful tool for this is it forces us to make what is normally in dynamic language land pretty implicit, to make it more explicit so we're thinking it through. All right, so now yet another value object. World needs more behavior. Whenever a lot of behavior starts getting into value objects like this, I'm naturally suspicious of it. But that said, the type of behavior that's good inside of a value object when you're practicing discovery testing is something that elucidates or gives you more information about the data that it contains. And so this is a good example of that. We have a world, and we just need it to provide us some data. And it should be as simple as getting it out of a map or something. So we can ask for the contents here. And I could test drive this, but I'm being lazy, so I'm going to just create a intentionally private map called for coordinates, give me contents, called my population. Seems reasonable. Why not just instantiate it right in place, since every one of these worlds is going to have one and none of them are going to have it provided to them. All right, so every world has a population. Every world can get you the contents at a point. So that means that at is called, I'm going to call it get coordinates. Okay, that seems legit. It means I need a way to set these coordinates, but remember we have two types of worlds. The one where like when you ask for any given coordinate, it's generated, and then the like the seed world in that case. And then the second kind of world, which is where we're like actively setting the stuff on the world. So already this at is maybe not helpful because in this case of the seed world, the implementation for at is going to be very different. So I'm going to go and take yet another deviation, make this an abstract class, specify that this method needs to exist. I'll copy this one first. All right, that's going to break a bunch of stuff. So in the meantime, we need a value that represents a mutable world. We can deal with the seed world stuff later. So I'm going to call it mutable world extends world. We're going to want to make, I did it again. Okay. This is going to want to be protected now. And our implementation of @ is going to look like that. And I can already be certain that I'm going to want to be able to set particular things. That's what makes this mutable. So there needs to be another method that is void. We'll just call it set, and we'll just delegate to the map. Okay. Is it put? Probably put. All right, cool. Okay, well, now we have some slightly more robust value objects that we might be able to use in this test. It also is going to break our other test now. So let's go up, top down, start fixing stuff. World being abstract can no longer be instantiated. Rerun this test. Okay, so the top level stuff still is happy with us. It doesn't need to know the difference between these types of worlds. That's good. This one is also going to only want to instantiate mutable worlds. Import. Okay. So let's keep on trucking. So outcomes have contents. Where were we? I call replace on the world with world 1 and 42, and the time limit is going to let me replace exactly one cell before quitting out. Then my assertion is that at the origin coordinates, which is going to be that first cell that we test, or that we transition, not that it is world 1, but rather that it is the contents that we want. So those contents won't have the same sort of equality check. Each one's going to be tested only for equality based on identity. So that means that we need to save this off. Next contents. What do we call that here? We call it contents. Let's call it next contents, so it's clear that like there's this generational divide, because it's also ultimately going to need neighbors. All right. Run the test. See it blow up in probably lots of ways. Returns null. So now we got our work cut out for us. We need to go and pull in now the dependency replaces cells. Cell. Ugh. So when time's not up, I know I'm going to be calling this method, replace coordinates. At this stage, they can just be these, because we're only doing one iteration now. And the world that we pass in is going to be the old world. All right, this is going to give us back an outcome object. Okay, and the outcome will give us next contents. There it is, which we want to set on a new world, which means we need a new world up here. So world, new world equals new. Now this is, we know to be an immutable world, and in fact, because we're going to be calling it set method, we need to actually make that type apparent. So now our next step here is call through to the new world and say set, hey, for those coordinates, yeah, I'll inline this again. Or not, outline, I guess. Okay. Starting at origin, we will call replace for those coordinates in the old world, get back our results, set them on the new world that we have. And that doesn't deal with iterating over multiple pieces of work, but we know time's up going to get at least called false the first time around. Alright, something didn't get satisfied. What was it? Definitely going to scrub super fast. Alright, well, that's a lot closer. And now we know that the first test that we had wasn't all that good of a test to begin with. And I don't know how much I care about this test. We could just have it near these assertions. Okay, so throw these. Original contents in place just to make sure that we get the same thing back, indicating that nothing changed. Oh, but it's returning a new world. Well, this is an interesting problem. So if we don't have time to replace a single cell, then it means that we're getting back an empty world. And I don't know if that's entirely a bad thing, because simply copying it and returning it would be dishonest. So I guess that's just sort of a thoughtful reflection on what this thing should do when we don't have time for a single cell to be replaced. That's interesting. Well, in that case, back out that change. I really don't even know what I want to assert here, or if anything. So this test has caused me nothing but grief. So I'm just going to kill it, and it'll be tested incidentally through the other interactions. So run it again. Hey, look, that's the best way to get your test passing. All right. Things are going to get more complicated before they get easier. Now I want to test for 2 cells to be replaced. Now this is going to force me to think about the neighbor stuff. So that means that my outcome is going to need to also provide me with neighbors. And neighbors need to at least have coordinate types. So create a local thing called neighbors. I'm going to make it a collection of coordinates, I guess, to start. Array list is my default thing. I guess we're going to need at least one neighborly coordinate, so we'll just do like something else. It doesn't really matter what. I'll just pick some silly number. I'm going to do here arrays.asList new coordinates 50, 50. How about? Okay, so we have some neighbors. We have a new coordinate here, 50, 50. And we're going to return an outcome that contains both. So we're going to change this constructor to do both. Okay, gives us our neighbors. This dot neighbors equals neighbors. Okay, so now when we get back something, it'll give us our neighbors too. And we don't really care how, but we know we're going to want to loop. Oh, right. So this test implies that this is going to return false twice. Allow us to work on 2 different things. And then subsequently loop over. So when replace a cell is called at this, we get that outcome. We might need a second outcome. Whew, contents. Ugh, everything's a neighbor or something. So I'll just say next contents 2 equals new contents, so that I can have an outcome 2. I don't need to give it neighbors because it's, well, I'll just give it an empty array list of coordinates. We're not going to have time to process them. Doesn't like that. Seriously? An array list coordinates does not count as a collection. Java typing. All right. Make sure that I got the type straight. Neighbors 2 equals code ordinance. Yeah, well that's definitely not a thing. So the typing was right, I just misspelled it. Code ordinance. Coordinates? Oy. Paste this in. Aha! Yay, Java so easy. Alright, so next content's 2. Pass that in, the little squiggly lines telling me I got that wrong. Alright, so at 50-50, I want the new world result that at new coordinates, 50 very carefully spelled coordinates, is next contents 2. Alright. Huzzah, that's a good start. I'm missing a parentheses here. Okay, so this is definitely going to fail because we're not doing anything to check these. And I've got a failure up here because I'm not providing any neighbors, so I'm just going to end. Alright, here you go. First test, still passing. Second test, obviously, this is a long test at this point. This is like, you know, getting up to 15 lines or so. That does not portend positive things about where this method is heading. So, I think that what I want ultimately is a queue of work, a queue of coordinates to work on. Cells to replace, I guess. Maybe make it a new linked list, which implements the queue interface. Wonder if it takes an initial. Do you take an initial? Okay, it does. Cool. So in that case, I'm going to send it this first coordinate there, the origin. It's a little bit of a long line now. I'll full screen this. All right. So cells to replace, starting with just the origin. If time's not up, well, what I want to do is loop over each of these things. So while cells to replace has is not empty, I guess. While that's not empty, it won't be to start. Then if the time's not up, oh wait, and you know what? These are 2 Boolean checks that I can put in one place. So as long as this isn't empty and my time's not up, then I can do stuff. So my coordinates are going to come from popping off of the cells to replace. Poll. Poll and remove have slightly different definitions. What's the difference here? Returns null if empty. Well, we know it's not going to be empty. So we'll use the more constrictive one, which is remove, which will raise an error because that would definitely be an exceptional case as far as we care in this code. All right, so coordinates. Outcome, replace the cell at these coordinates. I don't know if we're going to need these coordinates again. Oh, we will, because we're going to set it on the new world. All of that to say, once we have this outcome, we need to go fill in new work. So, I guess the logical thing to worry about new work is after the old work is done. So that's done. I call cells to replace, add on the outcome, maybe add all. Is that a feature? Yeah. all the cells to replace. Oh wait, hold on. I just added it to itself. I add the outcomes neighbors, of course. Alright, now what? Let's double check that our stubbing at 50/50 was what we thought it would be. There's 50/50. When we replace the first cell, we get outcome 1. Oh, we never set up a stubbing for this one. See this? Outcome 2, unused, warning. That's not a good sign. So nothing was stubbing it, so it would have been impossible. So we need to go ahead and make sure that stubbing is available, get satisfied, and that it returns not outcome 1, but outcome 2. It's almost like copying and pasting a bunch of code is really error prone, so keep that in mind. Huzzah! So now we have that test proving this interaction works. So there's I shouldn't stop here, but I'm going to stop here. This has definitely gone on long enough. If I took more time with this, I'd start thinking, how do I extract some of this stuff? And this is, like I said, refactoring is an exception case. I shouldn't have rushed in and started allowing myself to start looping and thinking about queues and crap. I should have thought about like a new approach first, because now I'm in the same position I'd be with in Detroit School TDD all the time, which is like, what design pattern could I put in place here, and how could I pull this out? As it is, I don't see a really easy path forward, but I can predict that this thing's responsibilities are only going to grow because of how many vectors of change are represented inside of this object. For example, when I process a cell and its neighbors have already been processed before, this thing is going to be required to start deduplifying stuff. That's not good. So, all right. Well, we'll take a little siesta here. Call this the end of part 3, and figure out how we're going to take it next. Thanks for joining me, and I look forward to recording the next one. Bye.